Hello dear viewer, welcome to another episode of Lorenzo's Lessons of Space. This episode has in fact been requested by two of my awesome subscribers, James and Rule. Independently of one another, they have asked me how in fact it is possible, well not how it's possible, but how to rendezvous two spacecraft in orbit. They understand it's possible, but they want to know how to do it. So in this video I will be explaining precisely that. To this point, I put the probe 1 in an orbit here, and we have simulated one of the problems that a probe can have. Look, here it is, unpowered, all the things nicely deployed, and except the solar panels. We have zero electric charge, plenty of solar panels, but they have not been deployed, so at this point this probe is useless. To fix it, we have in orbit the repairman. And if we're going to switch to the repairman, we will see that it is a small spacecraft with an astronaut, Bill Kerman. Let's have a look. Are we just... there it is. It was all the way zoomed out. We have a small basic spacecraft here with a full tank of fuel and an engine. Nothing special here. It will rendezvous with the probe. Bill will deploy the solar panels and all will be well. Now, before doing this, we will of course look at the map. The repairman is in a low Kerbin orbit of about 280 kilometers, fairly circular and a little bit inclined. The probe 1 is in a much higher orbit. Now, to rendezvous these two spacecraft, and indeed to rendezvous any two spacecraft, there are three key points. Point number 1 is to be in the same plane, to share the orbital inclination around the parent body. You can imagine if we are in a 3D universe and this slice, this orbit, takes out one 2D slice of that 3D universe, we want these to be the same slices. You can imagine if you have the same orbit, but if it's tilted 90 degrees, you might only meet at 2 points and be at those points going in different directions, which of course makes any rendezvousing very difficult. So step number 1 is to match the planes. Step number 2 is to get into the same orbit, but with a twist. I'm going to come to that twist in a bit. We want of course to occupy the same orbit, because being at the same location as the probe, going at the same speed, will by definition put us in that very same orbit. Now we also want to get into the same orbit at the same place, and this is where things become difficult. It is fairly easy to just expand our orbit here and make the shape match this one exactly. If we just do that without thought, we will end up in the same orbit but at a very different place. And this is where orbital mechanics and space things are different than we intuitively guess they are on Earth. Imagine, for example, a freeway. A long road, straight or in a circle, doesn't really matter. There is a car and it is ahead of you. You want to catch up to the car, so what do? You accelerate, you go faster, and in due time you will catch up to the runaway car that you want to catch up with. Easy. If you do this way around in space, say you first get into the same orbit, see it as the road, but you're behind the satellite. If you then speed up, you're not catching up to it, you're getting into a different orbit. So imagine in our highway, our freeway example, that if you were to speed up, you would also be forced to take the first exit. Of course, you would never find the car you are following that way, and this is how orbits and space work, unfortunately. So what we want to do is first we want to match planes. That's straightforward, simple enough. Then we want to not immediately get into the same orbit. We want to get into any orbit that will put us in the same location as the target. So we want an orbit that intersects this orbit at one or more points, and we want to time this different orbit so that we will meet the target in space. Now, because we will be in a different orbit, we will be going at a different speed when we meet the target. So we're not quite there yet, but when we're close enough, we will then quickly as we can manage, change orbit, so that we will then, when we are at the same place as the probe, then occupy the same orbit, and then we will have successfully rendezvoused. So to recap, first we change the planes. Second, we make any orbit that will bring us in the vicinity of the target. this is not the same orbit as this one. This will be a different orbit. It will have a different shape. We will get near the target, and only then we will change our speed to occupy the same orbit, at which point we will be rendezvoused. I hope you're still with me. If not, don't worry, I'm going to do it now, which will hopefully make things more intuitive. First things first, set the probe as a target. This will give us some indicators. First and foremost of which we will be using are the ascending node and the descending node. Now, our planes are not horribly different, but they are a little bit different. You can see if I rotate the camera to have the target orbit in one dimension or two, we can see that our orbit, the blue one, doesn't exactly match. The ascending and descending nodes are the points where the planes intersect. So at the ascending node we are in the same plane, and on the descending node we are as well. And these points are also the location where we want to perform a burn to match the plane. So we can put a maneuver node here, and for plane changes we use the red markers, the triangles. And we want to, let's see if we increase it this way. We plan a maneuver like so, and we can look at the descending nodes. If this number becomes 0, then our planes will have matched up, and we can see, let's have a look. You will notice that the ascending node will be a positive number and the descending node will be a negative number. For our intents and purposes, I think 0.3 will do it, but we're going to try and make this precise. So, you can see you're almost there when the ascending and the descending nodes switch. And if we put them like in the middle here, you will be almost perfect here. 0.0 degrees difference. And you can see our planned orbit will then match exactly with the target's orbit. Before going on, I will perform this burn. So, as we all know how to do, you find the blue marker on the nav ball, lock your spacecraft in that position, and then time warp to the point of that burn. So I'm going to do that now. Let's see, that's 10 more minutes to go. And once again, thank God for time acceleration. Now these plane changing maneuvers, you want to do them fairly accurately, because they will lay the foundation for your rendezvous attempt. Plane changes are generally the costliest maneuvers you can do. In this example, the ascending node and the descending node were at roughly the same altitude. If you have a choice between an ascending node and a descending node, where one is significantly higher than the other, always go for the highest one, because at that point you will be going slower, and it will cost you less delta V to change the plane. So now we have done it. We are now in the same plane as the target. All we have to do now is rendezvous with it. Well, easier said than done, of course, but the first step is to make sure that at least one part of the orbit will intersect with the target orbit. We can tell like this, we will never ever meet with the probe. So we're going to simply kick out our apoapsis to a height that is shared by the probe. So if we put it like that, we will at least every orbit have the same altitude as the target. This says nothing about position. So we're going to do that now, and you can see these markers have appeared. These will help us in gauging where the target will be when we are where the marker is. There's a lot of sophisticated math going on under the hood. I do not completely understand it, but all we need to know is that this marker will tell you where the target will be here. So when we are at this marker, the pink one, the target will be here along this orbit. So this is not close to a rendezvous yet, and it will also tell you how far the separation is. In this case, it's 4,000 kilometers, so not anything good yet. Not to worry though, this is only the first step. We are going to perform the burn again. Fortunately, we have time warp 2 minutes into the future, and permit this burn. It's 470 meters per second. We should be well able to do that. Now, those of you that have done rendezvous before will recognize that you can drag this node around the orbit and already make make it so that we meet the spacecraft here. We're not going to do that today. Today we are going to do it in easy steps. But you can use those colored rendezvous indicators to fairly accurately gauge where the target will be so that you can rendezvous with it. For now though, bear with me, I'm going to first get to the correct altitude and then play with the indicator. Right, so we should now be having an orbit. I overshot it a little bit. This is quite important. The way I like to do it best, my rendezvous, is to make the apoapsis or periapsis, doesn't really matter, but one of the apses from the orbit to exactly match with the target's orbit, and why will become apparent in just a moment. So we did this maneuver. Let's remove the node and time warp a little bit. We can see we are ascending here now towards the target. Our target, the probe, is now at the point that we will occupy in, what is it, an hour. So this is not a rendezvous yet. While we are getting out here, consider the following. The probe will have a period, a certain amount of time that it will take to circle around. We will have a period as well, but this way, because our orbit is smaller, our period will be smaller. By planning a burn at the apoapsis, we can modify our orbit and, of course, change the period. Regardless of where the target probe will be when we are here, it will be a definite known amount of time before it is here again. By changing our orbit at the same point, we can influence how long it will take us to be there again. 1 + 1 is still 2. You should be able to put these two bits of information together. By planning a burn on a point where you intersect the target's orbit, it will almost always be possible to get a fairly accurate intercept. So we're going to do exactly that now. We're going to drag this maneuver node slowly, and you can see that the rendezvous indicators are coming towards us at a rather sedate pace. So now we have here the purple one. We match them up. So what you want to do is to match up these rendezvous indicators. And what we have here is that after this burn, we will come within 18 kilometers of our target. So we can fine tune that a bit. That's 48 now. Fine tune that as best as you can. Generally, I like to go for anything under 10 kilometers. 7.8 kilometers. That should be fine. So to restate what we are doing now, we are occupying an orbit that's different from our target, but will get us at the same altitude once every orbit. At that altitude where the orbits intersect, we plan a maneuver node so as to modify our period to put the next time we are at that altitude to coincide with that of the target. Once we do that, and if we do it accurately, we will have almost rendezvous. We will then, as I explained earlier, occupy the same space, or at least the same 10-kilometer blob sphere area of space as our target, but we will be going at different speeds. Once we are that close, it is simply a matter of matching speeds, catching up to it or slowing down depending on what you're doing, matching speeds with the target, and then you should be in the same orbit mere kilometers apart. And when you're that far, then you can use more intuitive ways of rendezvousing, like pointing towards the target and firing your rocket engine. We'll come to that in a little bit. Now we are performing the planned burn. You can see our orbit is expanding to the dotted line here. And what I like to do now is to cut engines just before we are finishing the maneuver node, remove the node, and that will put us in the new situation where we have not quite yet set up an encounter. Then gently fire the engine again, and you can see the indicators are creeping together. You can see the separation decreasing, and then you just cut your engines when they are very close indeed. So cut it now, 56, just a dab of throttle, and they are creeping together. And if you did your plane change perfectly, you should be able to get it down to 0. Well, I probably didn't do it perfectly because it was at 3.4 and then it was increasing to 3.9 again, but 3.9, anything under 10 really is great. That will count as a rendezvous. I am now going to time warp until that actually happens, because you see, even though we did the burn now, we are still nowhere near the target. We are still not occupying the same orbit. We are in a smaller orbit, but because this one is ahead, this one will make the rest of its circle in the same time as it will take us to make a complete circle. So let's time accelerate forward to that joyous occasion and get the rest of the rendezvous in order. You notice that the indicator switched colors because the system, it gives you two intercepts. One that's first and one that's second, and as you move along your orbit, the colors are liable to change. Doesn't matter, the encounter is still set for the same distance and nothing has changed except the color of the indicator. So time warping the rest of the way there, and we can now move into the space scene where we can start looking around. Here we have our target. Notice that the nav ball here is now in target relative mode. It has three modes. Number one is orbital mode. You're in this mode most of the time. It's relative to the center of Kerbin, not the surface, and it will tell you your orbital speed, useful for most applications. Second mode is surface. It tells us our speed over the surface of Kerbin, useful when you're landing or taking off. And the third mode is the one we want now. This is the target relative mode. This tells us our speed relative to our target, which is here the probe. And we can tell that our relative speed is now 129 meters per second. The retrograde and prograde markers on the nav ball have also changed. Look, if I cycle through the modes, these indicators will jump around. Retrograde to the target now means retrograde to the speed vector, the velocity vector, relative to the target. So if I burn retrograde to that vector, I'm actually matching speed with that, because we want to kill this relative speed and be going in the same direction at the same speed as the target. But not quite yet. We want to do this when we are as close as possible, because remember, if we are occupying the exact same orbit, then we cannot get closer or farther away anymore without changing that orbit. So we want to establish that same orbit, which is the same as occupying the same space at the same speed, the closest we are to the target. So as you recall from this indicator, that will be 3.9 kilometers. So we are going to gently time accelerate until we are at 3.9 kilometers away from this target. Oh, there we go, 6.5. Relative speed is still about 130 meters per second. So we get to 4.2.1. This is good enough, and now we are going to fire our engine, pointed in the retrograde direction in the target relative mode. Now when we reach target relative 0, or at least 4.6 meters per second, we can observe, let's finish the job and get it to a clean 0.0 meters per second. There we go. We will observe now that the probe is at 3.7 kilometers distant and will remain there. And if we have a peek at the map view, we almost exactly occupy the same orbit now. If we unset the target, no, we won't do that, we can see here way farther in the orbit there will be a 1.8 kilometer separation, because these orbits are still mathematically, technically not the same. See, if you zoom all the way in, there is a slight difference. But for all intents and purposes, we have now rendezvoused. So what we now can do is point straight at the target and apply a little bit of thrust. For this we use the pink indicator. It will point towards the target. Excuse me, I'm now pointing using the indicator that points away from it. We want this pink indicator here. Point towards that and apply some speed. Not too much, because all this speed that we are going to apply now we will have to kill once we get there. So we are going to go for a modest 20 meters per second. Generally you want to keep this low because it's just wasted delta V. If you're this close you can get away with 5 or something like that, but then your approach will take a long time. We are now doing a straight line approach to the probe. And you will see this has changed our orbit minutely, but we will change it back as soon as we get there. You can see even the encounter system here plots us. We will make it within 100 meters in 2 minutes. So that is a pretty fine maneuver if I do say so myself. Already pointing the ship away from it, ready to once again cut the relative velocity so that when we are at 100 meters or even closer, we will have effectively rendezvoused. Consider that we are doing a straight line approach in curved space. The way an orbit works, you can describe space as curved. So if we go too slowly, say we go at 0.1 meters per second, we will drift apart because the difference between the orbits will be larger than the relative speed we imparted. So you want to go slow to conserve your delta V, but you don't want to go too slow so that you not make it there before the curvature takes over. These effects are less pronounced the further away from a body you are, or the smaller a body is. You will hardly notice this around Minmus, for instance. But there is also a reason why I did this rendezvous quite high above Kerbin, because if you're in low Kerbin orbit, this effect is fairly pronounced. You will have to do things quickly and efficiently. So if you're having trouble doing your rendezvous, do them in high orbit or try to do them around relatively light bodies. So for now I'm going to time warp a little bit to get close to the probe. See, we are here now at less than 300 meters, so it's time to zero out the relative velocity, and that will then constitute a successful rendezvous. Now if you want to dock, of course, this is the point from which you attempt that. Now these vessels, they don't have docking ports. We are going to EVA over to it instead, but once you are at this point, that you are at 150 meters distance with a 0.1 or a 0.0 meters per second relative velocity, at this point of course you start to align docking ports and clicking things together to build the space station of your dreams. For now though, we are, if I can find it again, that is, let's see, no, before going out, because this probe is completely dark and not visible, we are going to fly right on up to it. We're basically going to repeat the step I did before this, point straight at it, impart some speed, just 10 meters per second this time because we're already bloody close. Turn around, and before you hit the probe, slow your speed right back down. This is the intuitive way of getting somewhere, is pointing at it, burning, and then braking. In the large scheme of things this doesn't work, but when you're within like 5 or 10 kilometers even, that works just fine. So every time I press the EVA I lose it, but there we are. No, I hit the board key accidentally. I have to hit the space key to let go. Let's see, there is our probe. I'm just going to complete our mock-up mission and deploy the solar panels on that. If any of you after watching this still have questions about how to go about docking and rendezvousing, please do send them to me, if I've explained something wrong or in a way that it's impossible to understand. I would love to know that, but I hope that with this, let's see, extend the panels. I hope that with this video I helped you a bit to achieve all the dockings you ever want, and grant you a lot of success in your future space programs, like the one the Chinese space program is currently experiencing. They have their lander on the moon, and I'm sure the people at Mission Control there are very, very happy with that. Also, if you didn't know yet, your EVA Kerbals can in fact deploy solar panels so that your stricken craft don't have to remain stricken forever. So, heading back to our spacecraft just for completion's sake, and then that can feel free to, well, it has a lot of fuel. It could go to the moon, it could go back to Kerbin, it can basically do whatever it feels like. Anyway, this was Lorenzo. I hope you enjoyed, I hope you learned something, and I will next be starting my new series, which should be up in just a few days. I invite you to stay on board for that, or if you're not on board yet, if you're not one of my awesome subscribers, do so now, or at least if you think you'll enjoy more videos of me mucking about in space, and I would love to see you next time. So this was Lorenzo with a Lorenzo lesson of space, teaching you how to rendezvous and possibly dock, or at least fix a solar panel. Thanks for watching, see you next time, goodbye.